My name is Paul Hutchison, and welcome to my Physics 2211 Lab 2 report. For this lab, we will be discovering the drag force acting on a plate that is falling to the ground from the experimenter's hands. To do this, we will be using Newton's second law and the definition of drag from the previous lecture videos. For this experiment, we began in Tracker analyzing the motion of the plate falling in Tracker. Then we will make a model of the motion in GlowScript, declaring that the net force is equal to the force of gravity. We will then discover the drag force iteratively to find the drag coefficient that gives a final position in GlowScript similar to the one found in Tracker. We began by conducting the experiment using the Tracker software to find the time it took for the plate to fall to the ground. We calibrated the axis by setting the origin at the center of the plate before it was dropped, and angled it in the path of the plate's trajectory. The scale was also set using the experimenter's index finger. Note that there is some error in the experiment as the plate began to turn as it fell, making the drag surface non-constant as it fell. However, for the sake of this experiment, it will be ignored. The next part of the experiment was creating a GlowScript model where the net force was equal to the force due to gravity. This meant the mass of the plate was found to be 0.01097 kilograms, using a good scale. We then did the iterative step in calculating the ball's velocity and position using the respective update formulas as is seen in the GlowScript code. This is the graph made from Tracker and the gravitational models. As you can see, the gravitational model expects the plate to drop much further than the actual model did in the same time. Hence, there is some drag force causing the plate to fall at a slower rate. So how did we proceed to calculate that? We used this formula. The formula for drag was found in the pre-lecture videos. This formula was put into GlowScript and added to the net force, and B was changed until the final position in the model was close to that in the Tracker results. The best approximation for B was 0.0773 Newton seconds per meter. The final position in the model with drag is only 0.03 meters, different from the actual result. Hence, this approximation for the drag coefficient is fairly good. Here you can see the chart that includes the data set from where the drag is added to the net force. We see that the coefficient of drag is approximately 0.0773 Newton seconds per meter using the formula for drag mentioned in the pre-lecture videos. We know that the terminal velocity is achieved for this system when the velocity is equal to the gravitational force divided by the coefficient of drag. Hence, to check if that is achieved for this system, we place a condition in the loop to check that equation in the model of the plate. Terminal velocity is not reached for this system as it is not falling for a long enough time. If there were to be an initial downward velocity, throwing the plate downward with that initial velocity would cause the plate to slow as it fell due to the drag force being so large. However, the system still does not reach terminal velocity even with the plate thrown downward, but it does show that the terminal velocity for this plate is approximately negative 1.41 meters per second. That is the end of this lab report, and thank you very much for listening.